My name is Sam Anderson, and I'm a postdoc at Simon Fraser University. I think about how short-term warm events like heat waves influence river flows, and I approach the problem from a data-centric perspective that I'm looking forward to sharing with you today. Heat waves matter for rivers. My personal inspiration was living through the June 2021 Western North American heat wave, where a week of temperatures up to 20 degrees Celsius warmer than normal drove a highly variable streamflow response. Basins with snow to melt at the heat wave onset responded by rapid streamflow increases, in some cases achieving all-time record flows. While after the heat wave, basins experienced very low flows unless they had glacier runoff as a buffer. However, warm anomalies are very broad categories of events. In November of 2021, a series of atmospheric rivers delivered over 200 millimeters of precipitation in BC. Importantly, this event was anomalously warm in addition to being anomalously wet, about 4 degrees warmer than normal as measured in Vancouver. Because it was warm, most of the precipitation fell as rain, and the early season snowpack also underwent substantial melting. In other words, those few extra degrees went a long way in shaping how this event played out. These two events were very different, but they share a similar context. They were both multi-day warm anomalies, and their impacts were strongly influenced by their timing relative to the 0 degrees Celsius transitions. Their anomalous warmth was enough to favor rain versus snow in November and drive excess melt in June. We can expect that one impact of climate change will be that there will be changes to the periods of the year during which warm anomaly events like these can drive a streamflow response. Further, we expect there to be more frequent and more intense multi-day warm anomalies like heat waves. Given that context, today I'll ask two questions. First, I ask, how are streamflow responses to warm anomalies empirically linked to the 0C transition timing? Then I ask, how does the timing of the 0C transition change under warming? Here, I use analytical models of temperature to derive the sensitivity of key metrics that govern the streamflow response. Importantly, I analyze these lengthened sensitivities across normal, warm, and hot events to understand how the streamflow response to heat waves may change differently than the streamflow response to more moderate conditions. So let's begin by considering empirical links in question 1. We use the Caravan dataset, of which the Canadian subset includes over 800 basins that have streamflow observations between 1981 and 2020, and that also have basin average temperature and precipitation derived from ERA5 reanalysis. We then define 3 event classes, visualized here for a single basin, where hot events are defined as at least 3 consecutive days where temperatures exceed the seasonally varying 80th percentile of temperature. Warm events are between the 60th and 80th percentile of temperature, and normal events are between the 40th and 60th percentile of temperature. We identify all of these events in the historical record at each basin over 40 years, and then we see how streamflow behaved during each event. Here is 1 year in one basin with events highlighted. We calculate the increase in streamflow during each event, the event duration, and the event temperature. Then, for each event, we calculate streamflow sensitivity, defined as the ratio between the streamflow response and the event duration and temperature. This sensitivity is a metric that summarizes the overall processes acting to generate river flows during an event in a basin. We can aggregate the sensitivity beta through time for normal, warm, and hot event classes. Here are shown 3 sensitivity time series for each event class at a single basin. We see that hot events drive streamflow in autumn and spring, as indicated by the bimodal curve, while normal and warm events drive streamflow primarily a little later in spring. So these are results at one basin, but we can aggregate over many basins to see if these patterns are consistent. And we find that this bimodal pattern appears across many different basins, and the key characteristics of the temporal structure have relatively simple explanations. The autumn mode turns off when the event temperatures transition to be sub-freezing. This happens later in fall for hot events, as hot events remain above freezing for later into the cold season. The spring mode then turns on when the event temperatures rise again above freezing. Similar as before, this timing occurs earlier for hot or warm anomaly events. And finally, the spring mode turns off for all three event classes when basin snowpack becomes depleted. We can summarize the controls of the bimodal character with three metrics: T-, which is when temperatures drop below freezing, T+, which is when temperatures rise above freezing, and delta, which is the duration for which event temperatures are sub-freezing. We can think about climate change then by considering how warming temperatures drive a shortening of the sub-zero portion of the year, and how this reduction may be different for different basins and event classes. This brings us to question 2, where we ask, how does the timing of the 0C transition change under warming? And how sensitive is this timing to warming for different event classes? To get into this, let's start with an idealized model of temperature written as a sinusoid here defined by its mean, amplitude, and annual frequency. We can analytically solve for the 0C transition timings, the duration below freezing, and by taking the partial derivative with respect to mean temperatures, we can analytically solve for an expression of the sensitivity of delta to warming mean annual temperatures. This expression tells us that if mean temperatures warm, then delta is reduced. Each basin spends less of the year below freezing. But the reduction in delta is greatest in the warmer basin, and this is because the slope of the temperature curve is more shallow at 0 Celsius, and so a small amount of warming can have a larger reduction in delta. This becomes a powerful and useful lens when we return to our problem with normal warm and hot events. A hypothetical basin might look like this, with median daily temperatures shown in blue and the 90th percentile shown in red. If there is a small increase in mean temperatures, then there's a change in the timing of the 0C transition, and there's a larger change in the transition timing for the hotter temperature percentile. Put another way, if there's a small increase in mean annual temperatures, then delta 50 decreases by a small amount, while delta 90 decreases by a larger amount. Looking at two real basins now, a colder basin on the left and a warmer basin in the middle, we can fit sinusoids to each temperature percentile level from median conditions to the 95th percentile. We can then estimate the sensitivity of the sub-zero period to warming for each percentile level, plotted on the right. We can see that in both basins, the sensitivity of delta to warming becomes more negative or more sensitive for hotter temperature anomalies. One key point is that at an individual basin, the sensitivity of delta for the 90th percentile of temperature can be very different than the sensitivity of delta for median temperatures. This tells us that changes to the hydrologic response to heat waves will be different than the response to less extreme events. Looking spatially at the difference between the sensitivity at the 90th percentile relative to the 50th percentile, we can see in darkest red that the coastal, southern, and western prairie regions have the greatest difference. Further, looking at the spatial pattern of the sensitivity of delta for the 90th percentile of temperature, we see again in darkest red that the coastal, southern, and western prairie regions are the most sensitive to warming. And now, let's tie this back to our streamflow storyline. Under small amounts of warming, this tells us that delta for hot events will reduce more than delta for warm or normal events. This means that the autumn and spring modes of streamflow sensitivity will become closer together in time, and that these changes will be more pronounced for hot events as compared to colder events. My concluding point is that under uniform warming, we expect that the streamflow response to more extreme events will change more than the streamflow response to less extreme events. This paper is in review at Earth's Future, and this topic has a lot more ground than I could get into today. So I look forward to questions and chatting with you outside of the session. Thank you.